Hey guys, in this lesson we're going to talk about asymptotes, more specifically oblique or slant asymptotes. Both of these names can be used. You're probably used to calculating or finding vertical and horizontal asymptotes when you're dealing with rational functions, and the typical IB example or IB math question will involve, for example, the quotient between two linear factors. That's a very typical exercise. Today we're going to do something different. For slant asymptotes or oblique asymptotes to occur or to show up, as you see, the degree of the numerator and the denominator, they need to be different. And that's exactly what we're going to have in front of us in a few minutes. But first of all, let's go back to the definition of an asymptote in the first place. An asymptote describes the behavior of a function as x approaches positive infinity or negative infinity. And for rational functions specifically, which we're calling here r of x, so the quotient between some p of x and some q of x, the degree of the numerator and the degree of the denominator, they will define the type of asymptote that we have. So from now on, we're assuming that we have a rational function in front of us, which is the case for IB math exercises. The ones, of course, that deal with slant asymptotes. So let's consider the following rational function. R of x is equal to p of x over q of x. We have three possibilities here. Number one, the numerator degree is the same as the denominator degree. And as I mentioned, this is the typical easier exercise in IB math. So for example, you might have a function which is 3x plus 1 over x minus 2, just to use a simple example. Now in this case, we're not going to have an oblique or slant asymptotes because the degree of the numerator is exactly the same as the degree of the denominator. What we actually have here are two asymptotes, a vertical one and a horizontal one. The only case where we're going to have a slant or oblique asymptote is when the degree of the numerator is 1 unit higher than the degree of the denominator. So for example, you have a quartic in the numerator and a cubic in the denominator. The reason for that is going to be more clear once we get to the example, and actually once we do it, once we go through the process of finding the oblique asymptotes, that's going to make it very clear as to why that's the case. The only case when the degree of the numerator is 1 unit higher than the degree of the denominator. Now, let's analyze all the other possibilities first, which are degree of the numerator is equal or degree of the numerator is smaller than the degree of the denominator, so we can get to the slant or oblique asymptotes later. So going back to this example, we do have a vertical and a horizontal one. The vertical one can be found by making the denominator equal to 0. So x minus 2 equals 0. Therefore, x equals 2 is the equation of the vertical line, the vertical asymptote. Now, to find the horizontal one, you can either focus on the coefficients of x over here, which will prevail as x approaches positive or negative infinity, or you can use a limit for that. If you want to be more precise or more sophisticated, you can indeed use a limit. So the limit as x approaches either positive or negative infinity, it's not going to change, of 3x plus 1 over x minus 2. Using L'Hopital, we have the limit of the derivative of 3x plus 1, which is 3, over the derivative of x minus 2, which is 1. So we have 3 over 1, which is just 3. Therefore, y equals 3 is the equation of the horizontal asymptote. Now, if you've never heard of L'Hopital, you can get to the same place by factoring out 1x, both from the numerator and denominator. So we have in the numerator x times 3 plus 1 over x, and in the denominator, x times 1 minus 2 over x. These x's, they will cancel out. And what we're going to have is the limit of 3 plus 1 over x over 1 minus 2 over x. Now, when x approaches positive or negative infinity, these fractions, they will approach 0, given that you're dividing a number, an integer, by a gigantic number, that being positive or negative, it doesn't matter. They're both going to approach 0. So this guy approaches 0, and the bottom one, it does as well. Therefore, we get the same thing, which is 3. Therefore, y equals 3 without using L'Hopital is our horizontal asymptote. Now, if you want to sketch this curve, you can start by placing the vertical and the horizontal asymptotes and by finding the x and the y intercepts, which are found by making or substituting x by 0 in the case of the y-intercept and y by 0 in the case of the x-intercept. These give us 3 times 0 plus 1 over 0 minus 2, so negative half. Therefore, the point of intersection with the y-axis is 0 comma negative 1 over 2. And by equating our function to 0, we get 3x plus 1, which is equal to 0. Therefore, x equals negative 1 over 3. So the point of intersection with the x-axis is negative 1 over 3, comma 0. So these are the intersections, and this is our graph. And there we go. Now, I know we didn't even start talking about oblique asymptotes, but I guess a little review doesn't hurt nobody, right? So let's get to case number 2, where the degree of the numerator is less than the degree of the denominator. What happens in that case? Now, if the numerator degree is smaller than the denominator degree, what's going to happen is whatever's in the bottom, which is the polynomial of the higher degree, is going to grow much faster compared to what's in the numerator. So picture, for example, a rational function where p of x is of degree 7 or of the 7th degree, and q of x is a polynomial with degree 8. When you evaluate the limit of this rational function, this number will become much bigger, much faster than this one, and the limit will be 0. Therefore, we do have a horizontal asymptote, which is y equals 0, so it does exist, but there's not going to be any oblique or slant asymptotes. What may show up also are vertical asymptotes, whatever makes q of x equal to 0. So if, for example, q of x is x squared minus 4, there are going to be two vertical asymptotes, positive 2 and negative 2. But it may also be the case, of course, that there's no vertical asymptote. Now, on to case number 3. Now, for case number 3, we have the situation where the numerator degree is greater than the denominator degree, and we're going to analyze a very special case within this subset of types of rational functions, which is when the numerator degree is higher by 1. So it's 1 degree higher, and this is exactly where oblique asymptotes or slant asymptotes, where they show up. Now, I couldn't continue before answering the following question. What if the degree of the numerator is higher by more than 1? If it's higher by 2, then we have a parabolic asymptote. If it's higher by 3, we have a cubic asymptote, but we don't need to talk about those cases because they're not going to show up. So going back to the case that we actually should know how to solve, which is the degree of the numerator is higher by 1. Why is it the case that in these situations, an oblique asymptote or slant asymptote, it shows up? It shows up because after you go through a polynomial division, after you divide these numerator and denominator, or the numerator by the denominator, what you get is a linear term plus some remainder, and that linear term represents the direction the rational function follows at infinity. It's going to be more clear after we go through the process itself. So it all reduces to a long division. Now let's say that your rational function is 2x cubed plus x squared plus x plus 3 over x squared plus 2x. Now, in this case, as we can see, we have a difference of 1. This is our p of x, and this is our q of x. And how do long divisions work? If you're trying to divide some p of x by some q of x, where the dividend is p of x and the divisor is q of x, we are going to get some quotient. And let me change this q to something else so I can use q over here. All right, so I changed it to d of x. So our divisor is d of x. Now we get some quotient, which we're going to call q of x, plus the remainder, which is r of x, over the divisor. It didn't get divided by d of x. It couldn't. It is the remainder. And the layout in a long division is the following. We have the dividend over here, over the divisor, which goes over here. We're going to get some quotient, which is our q of x, And after going through a long division, we get the remainder over here. So this is a typical layout. As you see, the slant asymptote will show up over here as the quotient. Now, performing a long division between 2x cubed plus x squared plus x plus 3 by x squared plus 2x, we get 2x. Remember that you need to subtract whatever you get for this product right here from the 2x cubed plus x squared plus x plus 3. So 2x fits perfectly here. 2x cubed plus 4x squared. And after subtracting, we're going to have negative 3x squared plus x plus 3. And now proceeding to the next term, which should be negative 3, we get negative 3x squared minus 6x. Therefore, our remainder is 7x plus 3, which means that r of x, which was written like this, can also be written as quotient 2x minus 3 plus the remainder 7x plus 3 over the divisor x squared plus 2x. And this is our slant or oblique asymptote. You can plot this curve to observe, to check the result. And here we have both the function r of x and the slant asymptote 2x minus 3, which is right here. And we can definitely see asymptotic behavior. Now, the most important question to answer is why. Why is it the case that when you have a rational function where the degree of the numerator is 1 higher than the degree of the denominator, we get a slant or oblique asymptote? And also, why is the oblique asymptote the quotient of that long division? Remember that we can find these asymptotes with limits when x approaches positive or negative infinity. So let's evaluate the limit of r of x. So calculating the limit of r of x as x approaches positive or negative infinity is equivalent to finding the limit of this expression right here, which is the same after you run a polynomial division as 2x minus 3 plus 7x plus 3 over x squared plus 2x. Now, for this term, the degree of the denominator is higher than the degree of the numerator, which means that when x approaches positive or negative infinity, as we saw above in the other exercise, in the other case, this approaches 0, which means that all we're going to have left is 2x minus 3.